So I'll go link those two, today's video and Friday's video. But yeah, you might be able to find it if you search for my YouTube channel. Yep.
Say chapter 4, but chapter 4 is a polynomial.
Polynomial rings. Yep. Okay, so for today, questions on any of the homework? I know some of you have been needing extensions for a day or two on some of that homework. And I'm not caught up with grading, so I've got some grading to do today and tomorrow. Any questions on homework or anything like that? I do have office hours tomorrow. If you need to meet with me at a time other than my office hours, I'm pretty flexible in my schedule, so I can try to find a time to meet with you if you need that. Okay, we'll just keep rocking and rolling. Today I wanted to prove like 4 theorems that are kind of short and then do a bunch of examples. So this is kind of the plan. So let's start by defining homomorphism. We've kind of talked about homomorphism as like part of isomorphism, but I wanted to define it by itself. So the definition of homomorphism is here on page 75. Down. So let R and S be rings. A function from R to S is said to be a homomorphism. If it satisfies these properties, f of A plus B equals f of A plus f of B, and f of A times B equals f of A. So there's our definition for all A, B, and R. Okay. So there's our definition of homomorphism. So I want to give you 4 mappings, and I want you to decide in your groups whether these are homomorphisms or not. Okay, do these satisfy these definitions or not? Okay, so here's one. Real numbers, sorry, R. So this is defined by f of x equals square root of x. This one is, I'll call it G. I'll use different letters so we can talk about them. Do you know what this notation means, 2R? So 2R is this ring. Oh wait, should it be 2Z? Wait, 2R doesn't make any sense. It should be 2Z. I think I wrote that down wrong. Because 2R is the same as R. Yes. So 2Z would just be the even numbers, right? So 2Z is just even numbers. Okay. So there's G. Okay, and then let's say H is this map from R to MR, and this is the ring of 2 by 2 matrices with entries in R. So that's the notation we've been using for that. Okay, and here's how H is defined. H of A equals negative A, 0, A, 0. Let's see, I'm running out of function names. Let's say K is this function name. And K goes from Z mod 12 to Z mod 4. And here's the way that mapping is defined. K of some element in Z mod 12 is equal to, you take that same element, but you just take it mod 4, right? So there are our 4 mappings. And so I want you to, oh, did I define G? I didn't define G. Sorry, let me define G. G of X equals 3X. I'll do, maybe I'll divide the board this way. So you can see them. There's four things. So let me show you people who are online what these are. And y'all can go ahead and get started on those. Deciding if they're homomorphism or not. So the first one is just from R to R, and it's the square root of X. The second one is here. It goes from the evens to the evens, and it's G of X equal 3X. The third one is here. It goes from the reals to the 2x2 matrices, and it's defined as H of A equals this matrix, negative A0, A0. And the last one is goes from Z mod 12 to Z mod 4. And you just take any element in Z mod 12 and then just take that element in mod 4. And that's the mapping. So we're trying to decide which of those mappings are homomorphisms, which are not homomorphisms.
Yeah, if they're different, it does. Well, I mean, if it's so. Oh, wait. Well, if we cancel out the A squared on the side, if you have like the square root of 5, the square root of 4 is the square root of 5.
So go ahead and talk to the people around you if you haven't already. You three want to talk together? And then you four, maybe Peyton, you can flip around. We're just looking at these 4 mappings and trying to decide if they're homomorphisms or not.
Okay. So F of A, B, A, and B are both 4. Then this would be 6. This would be 4. This would be 16. This would be 16. Then 3 plus 10, 4 times 4 would be 2.
Or this, or this like it works. Or
I feel like that's
Yeah, that. Yes.
Yeah, if B was
That's a good.
the negative opposite.
That's a good point. Because if you wish to-
Okay, so as you're doing this, really, you're just checking these two properties for each one, right? That's all we're looking at. And if you get the feeling that it doesn't apply, you just need to find a counterexample. You can find an A and B for which it doesn't work, right? If you're thinking it's not gonna work.
If you just show that A and B aren't equal on both sides, does that work? So they're putting in like.
You mean it that this and this are not equal on this side?
Yeah.
Yeah. Yeah, so you can show it in general, or you can find a counterexample. Which one are you all on? Maybe, okay. You all have time to show all four of them? Or still working?
Yeah.
If you're not sure how some of these mappings work, you could try plugging in some elements and seeing what happens. I mean, I think you're probably familiar with square root X and 3x, but the one with the matrices and the one with the modular is picking, you might be sure exactly what's happening.
Why is 12 supposed to be like, it doesn't matter what the fix, like, this division of room, this is the way that matters for mod 12. And you can still get them to be the same thing mod 4, like, you can just have a multiple 4 instead. You still have the same thing out here, so it still adds, it still multiplies, there's still this.
Yeah, I think you're right. I think you also should just addition information.
Correct, that's not necessary. Yeah, I think this, well, I think this is just verbatim how you should do that.
Yeah.
It starts as-
It's never happened.
Okay, we're ready to talk about at least the first one of these. Okay. What was your feeling on this? Is it going to be a homomorphism or not? The square root of X? You're thinking no? Where does it break down? Addition or multiplication or both? addition breaks out? Okay, how so? What is that?
Root 2 plus root 2 is not root 4.
Okay, so if I had, f of 2 plus 2, you're saying that's not equal to f of 2 plus f of 2?
Yeah.
Okay, so this is, the square root of 2 plus 2, which is square root of 4. And is that equal to square root of 2 plus square root of 2? So none of these qualities are gonna hold.
Yeah.
So this is like what I meant by a counterexample, where I have specific numbers there that I plugged in and showed that that didn't work. Did anyone have a different way of showing it or saying it? Okay. What about this one? Is this gonna work with the homomorphism? No? No? What's the problem here? Does addition work? Addition's
Yeah.
okay? Multiplication is the problem?
Yeah.
Okay. So what happens when I do g of, I can just do it in general, x plus y, or x times y? Well, that's equal to 3 times x times y, but if I do g of x times g of y, I'll have an extra 3 in there, right? So I get 3x times 3y, and those two things are not equal. So it's not gonna be a homomorphism. So like I said, we can write our conclusion. What about this one? Is this one gonna work out? Also no? What's the issue here? The multiplication doesn't work out. So if I do h of AB, that gives me negative AB 0, AB 0. And if I do h of A times h of B, I get negative A 0, A 0, negative B 0, B 0. And that gives me multiplication positive AB. So is that it? 0, 0. And I get negative AB? Yeah. Like that, right? Yeah, so it's not, those two are things are not equal. So this is not a homomorphism. Are they all not homomorphism? Okay, and does this one work? No? Yes? Not sure. Okay. All right. So what is k of x mod 12 plus y mod 12? So that gives me, okay, so how do we prove this? Let's see.
We said that, I guess it's just the same thing as, because in modular arithmetic, it was like here in 3 point something says you can add and multiply in modular arithmetic.
I think it's just the definition.
Yeah, okay, what was we had a thing where we could go from like this notation to the other notation, right?
3.2.
Yeah, so this can be this, so in other words, this is the same thing as k of x plus y mod 12, right? So those inside things are equal.
Can you start going from the other directions if you say that like K like A mod 12 plus A B mod 12? And work it that way because.
Let's actually, you know what, let's start by like just writing down what this mapping is for everything. I think that might help, is just to kind of see what's happening here. So I'm just gonna write down all the elements in C mod 12. And then let's do what they map to on this mapping. So if I took 1 mod 4, or 0 mod 4, I get 0. 1 mod 4 is 1. 2 mod 4 is 2, 3 mod 4 is 3, 4 mod 4 is 0. And it's just gonna go through that again, right? So that's my mapping, so it just maps over to that. If I can remember, if I had X mod, if I had this. Okay, I'm trying to remember how we would say that. So if we had that X mod 12 is equal to Y mod 12, then we would write that as X minus Y is equal to 12n or something like that. Remember that? So that was kind of how we went back and forth between those things. So can we use, I'm not sure what, I'm trying to think about, I didn't actually write this out, but what notation might make sense to use here? Yeah.
I did it, saying, like division algorithm, I said X is 12i plus A and Y is 12j plus B.
Okay.
And then,
Yeah, and then you could kind of use that, right? So I think here what might be helpful is trying to break it down to go back to like real numbers and use addition and multiplication there, and then kind of bring it forward into the modular. That was kind of my gut feeling for how to write this down. So let's do that. So let's say X is equal to 12, 12K. Let's not use K, come on, J plus, what were you doing? Oh,
I just did 12i plus A. And then
okay. Yeah, I'll just use your notation, and Y equals 12J plus B or something like that, right?
Mhm.
And so A and B, so by the division algorithm, we can have that 0 less than or equal to A less than 12 and 0 less than or equal to B less than 12, right? Okay, and so when we take, if I take K of X plus Y mod 12. Okay, it gets tricky for, okay, so that's gonna be X mod 4 plus Y mod 4. Well, what is that? Well, that is gonna be, essentially X mod 4 is gonna be equal to A mod 4, right? Yeah, and Y mod 4 will be equal to B mod 4. I'm not sure if this is helpful or not. So I can write that as 12I plus A mod 4 plus 12J plus B mod 4, which is equal to, that's essentially A mod 4 plus B mod 4, which is A plus B mod 4. Right? Yeah, we get that from the,
Yeah,
we can add, we had a theorem that we can add things in modular arithmetic. Yeah, and this part goes away because the 12 is divisible by 4. That's a multiple of 4 there, and then that's a multiple of 4. And so then that's going to be equal to, well, maybe we go the other direction. We should say K of X plus Y mod 12 is equal to, well, what is X plus Y mod 12? Well, X plus Y is that plus that, right? So 12I plus A plus 12J plus B mod 4. Well, the 12I and 12J are going to go away because they're mod 4, they're zeros. So we're going to get A plus B mod 4, whatever that is. So those are end up being equal. You can do a similar thing for multiplication. But I think it kind of goes down to like thinking about them in terms of like the division algorithm and what's happening with remainders and so on like that. Does that sort of make sense? Okay. Anyway, yeah, so you just got to kind of have some notation to use. But all right, so that's good. So let's do these theorems that I've been putting off. So let's start with theorem 3.7. For theorem 3.7, we're just going to prove a bunch of theorems. So that says, theorem 3.7 says cancellation is valid in an integral domain. And so we've kind of talked about that some. If we have no zero divisors, then we can divide things. We can get rid of, we can do cancellation. So you actually don't have to have units. So I think because we kind of started with modular arithmetic, we kind of got in our heads like, okay, if it's not a unit, it's a zero divisor. If it's not a zero divisor, it's a unit. And that's kind of been stuck in our brains a little bit, I think. But you actually don't need units to be able to kind of divide or to have cancellation. And so we'll show that all you really need is no zero divisors. So, all right. So here's theorem 3.7. Okay, cancellation is valid. In any integral domain. What do we mean by that? What we mean by that is if A is non-zero and AB equals AC in R, would be equals to. Okay, so y'all can prove this. This one's not, it's like just a couple of lines. So what all do I need to assume here? Assume that A is non-zero and that R is an integral domain, right? Okay. Anything else I need to assume? What's the if part? I want to assume all of the if part. Yeah, I'm going to assume all of this stuff is what I'm going to assume. Right? I'm going to assume all of the if part, and I'm trying to get to the then part. Yeah. So we're going to also assume that AB equals AC. And then where do I want to go? What's my last line going to be? That's B equals C. Right, so that's the structure of my proof, the first and last lines. So let's fill it in. What do I need to do here? I've got this, right? So follow your nose. What do I need to do? I want to somehow use the fact that I have an integral domain, right? So I need like two things multiplied together equal to 0. So how can I take this and manipulate it?
Move the AC over.
Move the AC over, right? So I have AB minus AC equals 0R, getting closer than what?
Then use the distributive laws to take out A.
Yeah, so use the distributive law backwards to take out the A. So I have A times B minus C. And so since it's an integral domain, what does that mean?
A can't be zero.
Yeah, and I've already assumed A is not 0R. So what else is true?
B minus C equals 0.
Yes, so since R is an integral domain, and A is non-zero, we have that, that means, so the integral domain means that A is not a zero divisor, right? So you can't multiply A by something and get 0 unless that thing is also 0, right? So B minus C equals 0R. And then we just add the C over and we get that. Okay, pretty simple. So, so you see this type of argument we've seen many times the last few weeks. Okay. Let's see if you can get all the lines of that on the video. I haven't been great about, sorry, William, I haven't been great about showing everything on the video. Anyway, maybe you can hear what I'm saying and put it together. Okay, so theorem 3.8. Okay, so theorem 3.8 and 3.9 kind of go together. 3.8 says that every field is an integral domain. So if you have all the non-zero elements are units, that means we don't have any zero divisors. Okay, so so theorem 3.8 says that every field Okay. And so how are we going to prove it? Well, I want to prove that it's an integral domain, right? So how do I, so what is the property of integral domain that I want to prove? I want to show that there are no zero divisors, right? So what do I need to show here? How do I set this up? Well, I just need to take some arbitrary elements of this ring, right? And set it up so those arbitrary elements are equal, when I multiply them together, are equal to 0, right? And then I need to show that those two arbitrary elements need to both, one of them needs to be 0. Okay, so that's going to be my argument here. So, so we're going to assume that F is a field, and A, B are non-zero elements of F. Actually, maybe we don't need to make them non-zero. Maybe we just need to say A and B are elements of F with A, B equals 0. And then we're going to show that one of them has to be 0. So how about we do it that way? So assuming they were non-zero, that would lead to we'll get a contradiction if we do it that way. But I think we can just do it directly and it might be more clear. So let's do case 1. What are the possibilities? Well, if one of them is 0, then if A is 0, then we're done. Right? So either A is 0 or it's not, right? So if A is 0, then we're done. There's nothing to prove. Let's say it that way. So and if A is non-zero, then what do we need to prove here? B has got to be 0, right? So so now we have that AB is 0 and A is non-zero. And we also have that F is a field, right? So we need to use that some way. So F being a field is going to tell us that we have some, that every non-zero element has what? Yes, that's right. Zach, did you have a different way of saying that?
Oh, I was gonna say
What she said, yeah. So if A is non-zero, then and F is a field, what does that mean about A? It has a multiplicative inverse, right? So if A is non-zero, then since F is a field, oh sorry, this F, big F. A inverse is in F, right? So A inverse, that's my multiplicative inverse. So our notation for that is that A with the -1 there. That's my multiplicative inverse. Okay, and so what do we want to do? Well, let's start with B. And we're going to do a string of things until we get to 0. Okay, so what could I do? Well, I'm going to multiply by 1 in a creative way, right? So B equals B times 1R. How do I know that there's a 1 in there? Well, it's a field. It has a 1 in there. Okay, the field has a unit. And how can I write 1? What? A inverse? Yep. So it's B times A inverse. Now let's use our assumption. Do you see it? What do you see, Sebi?
The A's will.
Well, that's how we got the A's there. Yes, well, let's use something else. AB is 0. AB is 0. And since it's a field, does it commute? A field is commutative, right? So since it's a field, I can actually switch these. So let's do that first, just to kind of emphasize that we are in a field, we have commutativity. So this is AB, A inverse, I guess I could have put the one, well, anyway. So this is 0R, A inverse. And what's that equal to? That's the R. What did I get? I got the B equals 0, if A is non-zero. I kind of like that. I think that's good. Okay. So that's it. So that's in either case one of A or B is 0. So R has no 0 divisors. And why did I say it has no 0 divisors? Because I just chose arbitrary elements in F, right? I just chose an arbitrary A and B. So if any A and B that we pick, we're going to go through the same argument. Okay, so this holds for all pairs of elements in F. Oh, whoops, not R. We called it F before. We'll call it F now. Oh, should I have called this 1F? Maybe I should have. We can change all those subscripts to 1F. I'm so used to calling the ring R. I was calling them all R's. Boy, they're all over the place. There's one there. Okay. How about that? Yeah, go on.
Really quick, on that step where you switch A and B, do we have something about multiplication being commutative here?
In a field, it's a field. F is a field.
Oh, okay.
Yeah, you're right. But yes. Yeah, so that's why I wanted to emphasize that point that we can do that because F is a field. I think to be a field, it has to be a commutative ring with identity to start out with, right? So I think, let's see here, where's the definition of field? Field, where are you? Oh, it's back in 3.1. A field is a commutative ring with identity that satisfies that axiom. Yeah. So we have commutativity for a field. Okay. So our next one is theorem 3.9. This proof I find to be a little bit, I don't know, you might not like this. I'm not a huge fan of this proof, but anyway, we can do it. We can go through it. Okay, and so this proof 3.9 is that every finite integral domain is a field. Move my thing here. And I'm just really following the proofs from the book. So if, okay. Okay, so if you have a finite integral domain, then you have a field. Okay. So this proof relies heavily on the finite bit, okay? So what we're going to do is we're going to list out all the elements. So we're going to say, okay, if it's finite, it has n elements. So let A1 through AN be the distinct elements of this field. And then we're going to take an arbitrary one from the middle, and we're going to try to show it's got to have a multiplicative inverse. Otherwise, we're going to end up with more than n elements. So that's going to be the argument. Okay. So we're going to say, yeah. So if it's an integral domain, I think you already get that it's a finite, that it's a, does it have identity already? Okay, hang on, let me go back and look at the definition. Because I think all we really have to prove is the inverse part. Yeah, so integral domain already is a commutative ring with identity. So we have all that stuff for free. All we need to show is the inverses part. Okay, so flip back to where that is. Okay. Oh, I didn't ask you all, how are you liking the online textbook? Is it working all right for you? Do you use it?
It times out, which is annoying.
It times out? Okay.
But
yeah.
other than that, it's
Because
fine.
they were asking about for next semester, because this is the first time we've done the direct bill for the online textbook. And I kind of thought y'all would want paper textbooks because I love paper textbooks. But y'all are in a digital age, so maybe it's not the same thing for you. But you're liking having an online textbook? You prefer that? Okay, well, good. That's good. I'm glad it's working out. If you have any thoughts or comments about that we should pass on to next semester's classes or the instructors for next semester, let me know. That way I can kind of pass those words on. Yeah. Okay. Yeah, and the direct bill always scares me because I'm like, you're gonna charge it? You know, I don't know. It makes me nervous. Anything that's like directly charging me, I get nervous about. Okay. All right. So we've already got the commutative with identity. Okay, so we only need to show each non-zero element A and R has a solution that for each non-zero element A and R, there exists a solution to AX equal 1R. Okay, so how are we going to do that? So we can write. So we can assume. So since it's finite, I need to erase. So since R is finite, we're going to say R has n distinct elements A1, A2, up through AN. So here are the elements. I have written them out and enumerated them. Okay. Now we're going to pick one of them that's non-zero. We're going to pick one that's non-zero. So we're going to choose AT in R such that AT is non-zero. So this is going to be in general for any non-zero element. I'm just picking an arbitrary one, right? Okay. So to show this has a solution, what I'm going to do is I'm going to multiply all of those elements by AT, right? So I'm going to multiply all of those elements by AT. So consider AT times A1, AT times A2, up through AT times AN. And so what can we say about those guys? Well, let's think about it. How many of them are there? How many of these products are there? There are n of them, right? There are n of them. Are they distinct? Why are they distinct?
Because what you're multiplying by R.
Yeah, so there are n of these. And we can say they are distinct because of that. If AT equals AT-AJ, then what must be true? Then AI equals AJ because we have cancellation because we have an integral domain, right? So they have to be distinct because if they're not distinct, then the ones the list we started with weren't distinct, right? You see that? So we have n distinct elements, and so what must these be equal to? So since our ring is closed and it has n distinct elements, this must be a rearrangement of my n distinct elements. So one of them must equal 1R, right? So that's the argument. I told you might not like that. Do you like it? It feels fuzzy. But you can see like these are n distinct elements, right? I know that those elements are gonna correspond with elements in my ring R because my ring R is closed under multiplication, right? So there must be that one of these is equal to 1. Okay. And so we could maybe do that by contradiction. We're kind of doing this a little directly. And so we could maybe do this by contradiction and contradict that we have indistinct elements or that we, if one of these is not 1, then one of them must be equal to the other, but we proved it's not, or, so you could kind of, there are lots of different ways of saying that. But since we have indistinct elements, and R is finite and R is closed, we get that one of the ATAJs must be equal to 1R. So that's the deal. So that must have a so I picked an arbitrary non-zero AT to start with. So then that means that must be true for any non-zero AT. All right, that's that one. Theorem 310, I'm not gonna have time to prove it, but the proof is actually not bad. It's just a 5-part statement, and each of the 5 parts is kind of not so bad. So maybe I won't prove it, but maybe I'll have you read that proof. It's the same sorts of tricks we've been doing all along. And then we are basically done with 3.3 after today. So, so your last assignment, you either just read that proof, and then we're going to start into chapter 4 on Wednesday. So let me write down the statement of theorem 310. That way you'll have it. And then the proof, I was just going to follow the book, and it should be pretty straightforward. So. So if F from R to S is a homomorphism of rings, I'm going to list some things that we've been assuming to be true because we felt like in our gut it must be true. And in fact, they are going to turn out to be true. So the first one is that 0 maps to 0. So F of 0R equals 0S. And we saw that in examples, didn't we? We know 0's got to map to 0 or everything's going to break. What's the second one? F of negative A is going to map to negative F of A. And by negative, I mean the additive inverse, right? So if this is the additive inverse of A, then this F of A is the additive inverse of F of A, right? Negative F of A is additive inverse. Thirdly, F of A minus B is going to be F of A minus F of B for all A, B, and R. And this is for all. Okay, and then if R is a ring with identity, and F is surjective. Now that's important because that reminds us of our example. Remember our mapping where we took things mod 10, the even numbers mod 10 and mapped them, and we were looking at the mapping between Z mod 5 and those numbers, and where 6 ended up being an additive identity or multiplicative identity, right? That was not a surjective map, right? If you're mapping Z mod 5 into Z mod 10, that's not a surjective map. It doesn't hit everything, right? So in that case, 1 did not map to 1. We had a different one. But here, if we have a ring with identity and a surjective map, we're going to get that 1 goes to 1. Okay, so that's the next one. S is a ring with identity with So then you'll get 1 maps to 1. Okay, and 5, whenever U is a unit. We have that F of U inverse equals F of U inverse. So the multiplicative inverses map to multiplicative inverses, in other words, right? So these are the things you kind of expect to be true, but I wanted to point out here that the surjective part is the important thing there. If you don't have that surjectivity, it won't work, which we've seen in examples. Okay, so yeah, so the last thing for that section is just to read the proof of theorem 310. And that's it. So we are done with chapter 3 now. All right, see you all Wednesday.